So today what we're going to do is we're going to determine how to find the displacement from a velocity graph. And so a few things we need to review is finding the area of certain shapes. So here I have a rectangle, and a rectangle has 4 right angles, okay? And the area is equal to the base, which is this side right here, times the height. Now, some people say length times width, and some people say base times height. So this is base times the height, all right? And for this, a triangle, this is now called the base. And the height is always perpendicular to it. So this is the height. And the area of a triangle is 1/2 the base times the height. Now, this is a special triangle because it's a right triangle. And so this bottom side right here is the base, and this side is the height. So the 2 legs of the right triangle are the base and the height. So for this one, the area, I'm gonna put it right here, the area is equal to the base times the height, okay? And so we're gonna need to know the area, or whoa, I'm sorry, not base times height, it's 1/2 base times height. So 1/2 base times height, because the area of a triangle is always 1/2 base times height. Oh my, so okay. All right, so that's the review on the finding area of these shapes, and let's talk about some other things next. So I also want to talk about this, and this is the formula for average velocity, but we're gonna call average velocity for right now just regular old velocity. And this right here, this delta x, is my displacement. So what this is telling me is I need to get that by itself. So I'm dividing by the change in time. So I'm going to multiply both sides by the change in time. So that would give me v times delta t, which is the change in time, is equal to the change in x, which we're calling displacement, okay? So with that said, delta x is equal to v, the velocity, times the change in time. And so this is my, again, this is my displacement. Okay, and so we wind up with, if you find the velocity times the change in time, you wind up with the displacement, okay? So if you look at the areas that we just talked about, they involved a product of 2 things, right? So one of those 2 things, when we find these areas, one of them is going to be the change in time, and one of them is going to be the velocity, and that's what's going to allow us to find this displacement. So let's do a problem to help you understand this, and we're gonna build from a very simple problem that you could do without a graph, okay, to one that you would need to use a graph on, okay? So for this problem, we have a car traveling down a straight road. Okay, so this is one-dimensional motion, and it's traveling at 25 meters per second, and we're gonna go for 4 seconds, and then we're gonna find the car's displacement from that, okay? So we have the velocity, we have the time, so automatically we could, without this graph, go to finding my displacement, which is the velocity times my change in time. So in this case, my displacement would be my velocity, which in this case is 25 meters per second. So I'm going to take 25 meters per second, and I'm going to multiply that by 4 seconds. Okay, and when you multiply this, you would get 100 meters. So that's my displacement for this. It's 100 meters. So, okay, we don't need a graph for it, right? We could figure it out without the graph. But this is the graph of this velocity, okay? And it's 25, okay, for a period of 4 seconds, and it stays 25. That's why we have the horizontal line here, okay? So there's no acceleration going on, all right? So we're doing this without acceleration at first, okay? So what we're gonna do to find this, how this product is represented, is with the area between this line right here and the x or horizontal axis, okay? So if we find this area right here, that's represented by this product right here, because this is going to wind up being a rectangle. So I'm going to shade this in with a color, and then you don't need to watch me do that, and then I'll be back and show you how to do this. So this is how the area of this between the, again, between the velocity function and the x-axis or horizontal axis, how, if we find the area of this, that's going to give us displacement. Now here's why. Okay, so here's a rectangle, and this is the base, and this is the height. So for this, the base is right here, and it's from 0 to 4, so that represents 4 seconds. Okay, and that's where this comes in, okay? And then this part right here represents the velocity. And the velocity, we can tell this height is staying 25. So this is the 25 meters per second. So when we go to multiply, we multiply 25 meters per second times 4 seconds. We wind up with 100 meters. All right? So what happens if we have different velocities? Okay, so let's take a look. What would happen if we got had a negative velocity? Now I should say this is a positive velocity. So if we're talking about straight line movement and going like left and right, then this would mean we were traveling in the positive direction, which would be to the right, and we were traveling at 25 meters per second, and we did that for 4 seconds, which means we went to the right 100 meters. Okay. So what happens if we have a negative velocity? How does that show itself on a graph? And that's what we're going to talk about next. So for this one, okay, a car travels down a straight road at negative 25 meters per second for 4 seconds. So same scenario, but instead we're going to the left, okay? And so we can still do it just by the formula, okay? Our displacement is equal to our velocity times our change in time. So in this case, our displacement would be our velocity, which is negative 25 meters per second, times our change in time, which is 4 seconds. So this time our displacement would be negative 100 meters. Okay, so this is a graph of negative 25 meters per second over 4 seconds, and it stops right there. Okay, so again, it's a horizontal, but it's down below the horizontal axis because it's negative. So once again, I'm going to do the area, and I'm going to shade in the area between this, we call it a curve, but really it's a straight line, okay, between this curve and the axis, okay, so between these two. So it's all going to be right in here, and I'm going to shade that in, and again, you don't need to watch me, so I'll be back. So this time, I've shaded it again between the curve and the horizontal axis. And how does the area represent itself here? And how do we get this negative 100? Well, here's why. From 0 to 4, this is the base of the rectangle, right? And it's also the change in time. So my change in time right here is 4 seconds. Okay, so the height of the rectangle now is this value right here. And it turns out to be negative 25. Okay, so this is negative 25 meters per second. And so when we multiply these together to get the area of this, we wind up with negative 100 meters because this value is negative. So I don't want you to think there's no such thing as really as negative area, okay, because you can't have less than 0 area. But we can have what's called signed area, okay, and it just represents area that's below. So anytime, and this is going to be a key here, anytime the shape that you're trying to find the area of is below the horizontal axis, your heights are always going to be velocities, and so that velocity is going to be negative. So every time you find area underneath here, it's going to wind up having a negative value. Okay, all right, so let's look at a problem where we combine both of these scenarios. So this time a car travels down a straight road again, 25 meters per second for 4 seconds, but then it turns around and travels down the same road at negative 25 meters per second for 4 seconds. So what we should realize is that these should cancel each other out, because we went the same amount of time, we're going the same speed, and this would be going right, and then this would be going left. So what should happen is we're back to where we started. So this would be 100 meters to the right. This would be 100 meters to the left. We're back to where we started. So that means the displacement would be 0, because the change in position from the start to the finish of this, you wouldn't have changed, right? You would have stayed in the same spot. Now you would have moved, but the displacement would be 0, because the change in the position is, there is no change in the position. You're back to where you started at, okay? So once again, I'm gonna find the area between the curve and the x-axis and between this curve and the x-axis, okay? So I'm gonna shade that in, and then I'll be back. So I've shaded these in, and now I wanna take a look at this. One thing, I wanted to give you a problem here where like logically we could think it out without doing the graph, okay? So that's one of the reasons I picked this problem and built to get to this one, okay? Because we should realize just logically, hey, the displacement should be 0, okay? So once again, right here between 0 and 4, this base of this rectangle, okay, would be 4 seconds. And the height of this rectangle would be 25 meters per second. Okay, so this next rectangle, we went from 4 to 8, but the change in time here is 4, okay? So I'm gonna do this one down here. This is 4 seconds again, okay? But now this height of this rectangle, okay, would be negative 25 meters per second. So I'd have to combine, to get my displacement over the 0 to 8 seconds, all right, I'd have to combine both of these areas. So my displacement is equal to 25 meters per second times 4 seconds. And then I'd have to add to that the negative 25 meters per second times the 4 seconds. And so my change in position would be 100 meters plus, and then this would come out to be negative 100 meters. And when I add those together, my displacement winds up being, like what I think, 0 meters. Okay, and that should make sense to us, that it should be 0 meters. We went equal distance to the right and equal distance to the left. So okay, so I should have gone over this with the previous 2 problems. This means, okay, I went 100 meters to the right, and this means I went 100 meters to the left. I'm back to where I started, right? So 0 meters is the displacement. Okay, let's go to another one where the next problem, I've given you the position time graph and its velocity time graph that goes along with it, and show you we can do displacement both ways. And I'm going to show you that you get the same answer, whether you're doing it from like how we first learned from a displacement or from position time graph, or if we do the new way of finding it from the velocity graph. I forgot to say something before we go to the next problem. I need to say this, okay? Area below the horizontal axis will always be negative, okay? So I'm going to write that. So area below horizontal axis will be negative. Because the base will be positive, because that's our change in time, and the height will be the velocity, which has to be negative if it's below the horizontal axis, okay? And the area above the horizontal axis will be positive. Okay, and for the same reason on both of them, okay, if you have a graph that's above the horizontal axis, that means the velocity is positive. That's where you're going to get your heights for all your areas, and so those heights are going to be positive because the base will always be positive. And here's why: the change in time is always positive. We always take a later time minus the earlier time, which will always give you a positive value, okay? But I just wanted to make these two statements, okay? Area below the horizontal axis will be negative. Area above the horizontal axis will always be positive. And since these areas were the same but in opposites, that's why they canceled each other out, okay? So I want to do this problem because I want to show you that we're going to do it the same way. Okay, so this is the position graph, and this is the velocity graph that goes with this. Okay, so right here, the slope of this line right here, okay, it's an increase of 16 because we're going from 0 to 16, and we did that in 4 seconds. So 16 over 4 would be 4. That's why this is a horizontal line. The slope between any 2 points is 4 from 0 to 4, and that's why we're graphing this. Okay, so this one goes down, so we go all the way down to from 16 to negative 16. That's a decrease of 32, but we did that again in 4 seconds. So negative 32 divided by 4 is negative 8, and so that's why this is the velocity graph from 4 to 8. It's negative 8 the whole time. And then why is this on the horizontal axis? That's because there's no change here, right? So the slope of this would be 0, and that's why this is 0 from 8 until 10. All right, so we're going to break this up into chunks like we did before, okay? I want to do the displacement from 0 to 4. Now, I actually already said some of them, okay? So from 0 seconds to 4 seconds, okay? Well, we started at 0 and we ended up on the segment at 16, okay? So that's an increase of 16. So from 0 to 4 seconds, my displacement would be 16 meters, okay? From 4 seconds to 8 seconds, okay, we went from 16 to negative 16. Okay, so that's a change of negative 32, because if you go from 16 to negative 16, that's a decrease of 32. So my delta x, and you could do it this way too, we ended up at negative 16 and then minus 16. So negative 16 meters minus what we started at, which was 16 meters. And that gives us the negative 32 meters. Okay, so I also want to do from 8 to 10. From 8 seconds to 10 seconds. Okay, so for that time interval, the displacement would be, well, there's no change, right? Because we started at negative 16 and we ended up at negative 16. So that would be negative 16 meters minus negative 16 meters. And that becomes plus 16 meters. So our delta x for this case comes out to be 0 meters. Yeah, it didn't change position. It stayed at negative 16. Okay, so the overall displacement, okay, the overall displacement from 0 to 10 seconds, which is what we're really trying to find here, would be the 16 meters plus the negative 32 meters plus the 0 meters. Okay, now, what does that give us? Well, that gives us an overall displacement of negative 16. And I just realized you guys couldn't see this. Okay, so my displacement was 16 meters plus the negative 32 meters plus the 0 meters. And when I combine those, I get negative 16 meters. Okay, so that's how we did it, okay, from the position time graph. Okay, so let's compare that, because it should be the same if we use the velocity time graph to get this. Now, what do we have to do with the velocity time graph? Well, we have to find areas, okay? So I'm going to shade, okay? I'm going to shade all of this in between this straight line and the x-axis, and also between the x-axis and this horizontal line. And right here, I'm not going to be able to shade anything, right? I don't go up or down, right? Because there's no height to this, okay? There is a base, but there's no height to the rectangle. the area here is going to be 0, okay? I'm going to say that now. All right, so let me shade those in and I'll be back. Okay, so I've shaded them in, okay? To find this area, okay, this base would be 4 seconds. So this is 4 seconds. And the height would be this, and that would be 4 meters per second. Okay, for this one, the base would be right here. That's from 4 to 8. So the base here is also 4 seconds. The height of my rectangle would be this distance, which is -8 meters per second. Okay, and then this one right here, the change in time is 2 seconds, but there's no change in velocity, right? Okay, so there's no height to this. Okay, so you could do 2 seconds times 0 meters per second. Okay, you could do it that way. All right. So for my displacement on this one, I just have to accumulate all of these areas. Okay, so my displacement is going to wind up being 4 meters per second times 4 seconds plus -8 meters per second times 4 seconds plus, and then you could even do this one, okay, it'd be 0 meters per second times 2 seconds, okay? So my displacement is 4 times 4 is 16, so that'd be 16 meters, okay? And this would be plus, and -8 times 4 is -32, so that'd be -32 meters, and plus, and then this would be 0 meters, right? Okay, so look, okay, so this one came from the displacement here, but look what we got from 0 to 4. We got 16 meters also, right? And look what happened. We got from 4 to 8. We got -32. Here's -32, right? And what do we get from 8 to 10? 0. See how it matches up? Okay, so our displacement, our delta x, winds up being just simply -16 meters. And that's how you can get displacement from a velocity graph, okay? So once again, we've done these without any acceleration, right? So now I'm going to give you one that acceleration has happened, okay? So because what we've done up to this point is the velocity graphs have all been horizontal. What if they look more like this one, okay? That would mean that they have acceleration, like what we talked about yesterday, okay? Or the day before. All right, so let's go and let's do an example now, a full-blown example. So once again, okay, I have a cart. It's moving left and right along a straight line. The cart's velocity time graph shown below, okay? Find the cart's displacement between 0 and 6 seconds, okay? So my outputs, this is a velocity time graph. So just quick review. If we find the slope, that's gonna give us acceleration. But now, if we find the area between the velocity graph and the x-axis or horizontal axis, we're gonna get displacement. Okay, so there's two things. The velocity graphs are really important because they give us two things. They can give us acceleration, but they can also give us displacement, okay? So what I'm gonna have to do is I'm gonna shade this in, okay? So I have to shade everything between the curve, all right, and the x-axis. So all of this is gonna make a triangle right here. I'm gonna shade in all of this, okay? And then I'm gonna shade in all of this also, okay? Because that's the part that's below. Okay, so some of this is negative. Well, all of this is negative, and it's going to cancel out some of this positive. Okay, so this is the amount of distance that we moved right, and this is going to be the amount of distance that we moved left. Okay, so I'm going to shade this in, and then we'll start calculating displacement. So I'll be back. All right, so I'm going to have to get the area of this triangle. So from this point right here, from this vertex, I'm going to have to drop straight down to get the height. That's a right angle, okay? And so for this triangle, okay, this is gonna be my base, and it winds up being 3 seconds. And the height, that's this right here, okay? This height winds up being, we're going from 0 all the way up to 10. So this would be 10 meters per second, okay? Now, so that's going to get this area right here. Okay, I also need to get this area. So there's more than one way to do this. If you know the area of a trapezoid, you could. This is a trapezoid, and you could do that. I kind of doubt most of us remember that, but that's okay. So we could break this up into a little right triangle. Okay, so this is my right triangle, and then a rectangle. Okay, so that's how I'm going to do it. Okay, so here's 3, here's 4. This is right in between. So this little part right here, okay, is going to be from here to here. That is my base of my triangle, and it would be 0.5 seconds. Okay, now this would be my height, and okay, it goes all the way to here, and since that's in between -4 and -6, that has to be -5. So this height right here is -5 meters per second. And then, okay, so that's going to be this triangle here. Now we have to do the rectangle. Okay, so this rectangle, this base of the rectangle, well, it started at 3.5 and went all the way to 6. So that would be 2.5 seconds. And the height of this would be -5 meters per second. Okay, so I just need to accumulate all these areas and I'll have the displacement. Okay, so my delta x is going to be this triangle right here. So it's going to be 1/2 the base times the height. So I'm going to do 10 meters per second times 3 seconds. You know, I'm saying base times height, but I'm really doing height times base. Okay, it doesn't matter. All right, and then plus, and then this one's also going to be a triangle. So it's 1/2 I'm going to do the height, so that's -5 meters per second times the base, which is 0.5 seconds. Okay, and then I need to add this in, right? So plus the base, which is 2.5 seconds, times the height, -5 meters per second. So -5 meters per second times 2.5 seconds. Okay, so this one right here is the displacement between 0 and 3. This is the displacement right here between 3 and 3.5. And then this is the displacement between 3.5 and 6. Okay, and if we add all these displacements up, we wind up with the overall displacement. Okay, so half of 10 is 5, and then 5 times 3 is 15, and my seconds cancel. So this turns out to be 15 meters. Okay, and this one is half of -5 would be -2.5, and then -2.5 times 0.5 would be -1.25, so -1.25 meters. And -5 times +2.5 gives you -12.5, so -12.5 meters. Okay, and so if we add those up, our overall displacement turns out to be 1.25 meters. Okay, and that's how you find the displacement from a velocity graph. Okay, I'm going to add this. I said it, but I didn't write it. Okay, so this one right here, this calculation right here is the displacement between between 0 and 3. This one is this one right here is the displacement between 3 seconds and 3.5 seconds. And then this one is the displacement between 3.5 seconds and 6 seconds. And so we've added all those up and we get the overall displacement, okay? It doesn't get any harder than this. I mean, maybe some more areas you have to calculate, but that's it. It's all about area, right? And anything that's below the x-axis or time axis or horizontal axis, whatever you want to call it, okay? that's always going to be negative, and whatever's above is going to be positive, okay? All right, that's it, guys. That's the lesson for today. Hopefully you found it pretty easy and easy to understand, okay? So we'll meet back, all right? Take care.